Gravity is the first rule we learn without being taught. Long before we understand words or numbers, we learn that things fall. A dropped object does not hover. It does not drift away. It moves downward with certainty. This quiet behavior shapes every moment of life on Earth. Yet it is so familiar that it rarely invites curiosity. Gravity feels obvious. It feels settled. And because of that, it is easy to miss how strange it truly is. For most of human history, gravity was understood through its effects alone. Stones fell. The moon moved across the sky. The planets traced slow paths against the background of stars. These motions were regular, predictable, and deeply comforting. They suggested an ordered universe, one governed by rules that could be learned. This belief reached a turning point with Isaac Newton, who showed that the same influence guiding an apple to the ground also governs the motion of the planets around the sun. With a single mathematical description, motions on Earth and motions in the heavens were unified. Newtonian gravity was breathtakingly successful. It allowed astronomers to predict eclipses, chart planetary orbits, and send spacecraft across the solar system centuries later. Even today, it remains an extraordinarily accurate approximation for many practical purposes. Yet Newton himself was unsettled by what his theory implied. His equations described attraction acting across empty space, instantaneously, without any visible mechanism. Space itself was passive. Matter acted. Space merely hosted the action. This discomfort lingered until the early 20th century, when a deeper shift occurred. Albert Einstein proposed that gravity is not a force reaching across space at all. Instead, it is a property of space and time themselves. Matter and energy shape the geometry of the universe, and objects move according to that geometry. In this view, a falling object is not being pulled. It is following the most natural path available in a curved spacetime. This idea is subtle, but its consequences are profound. Space is no longer an empty stage. It is dynamic and responsive. Time is no longer universal. It flows differently depending on gravity. Clocks tick more slowly near massive bodies than they do far away. This is not a thought experiment. It has been measured directly. Atomic clocks carried on satellites run at different rates than identical clocks on Earth. Without correcting for this effect, navigation systems would drift by kilometers each day. Light itself responds to gravity. When it passes near a massive object, its path bends, following the curvature of space-time. This was confirmed when starlight passing near the sun shifted exactly as Einstein predicted. Gravity does not merely guide matter, it shapes the movement of energy and information. General relativity also revealed that gravity is not static. When massive objects accelerate, they disturb space-time, sending ripples outward. These gravitational waves were detected directly more than a century after they were predicted. Their signals matched theoretical calculations with astonishing precision. Space-time can stretch, compress, and carry energy across the universe. And yet, beneath this success lies an unease. The equations of general relativity are elegant and powerful, but they carry a warning. When gravity becomes extreme, the mathematics breaks down. At the centers of black holes and at the beginning of the universe, the theory predicts infinities. These are not physical objects, but signs that the description has failed. The theory that explains so much also tells us where it cannot go further. This is where the story truly begins. The unease deepens when we ask what gravity truly responds to. In general relativity, space-time curvature is not caused by mass alone. Energy contributes, momentum contributes, pressure contributes. Even forms of energy that have no rest mass still influence gravity. Light gravitates, radiation gravitates. In this framework, empty space itself can curve if it contains energy. Gravity is not selective. It responds to everything. This universality is one of gravity's most distinctive features. All objects fall in the same way when other influences are removed. a feather and a stone accelerate together in a vacuum. This principle, that gravitational motion is independent of composition, lies at the heart of Einstein's theory. It tells us something profound. Gravity cannot be shielded. There is no known material that blocks it. There is no way to turn it off. To exist in space-time is to participate in gravity. At the same time, gravity is extraordinarily weak. Between individual particles, its influence is negligible compared to other forces. Two electrons repel each other electrically, with a strength vastly greater than their gravitational attraction. Gravity only dominates when enormous amounts of matter and energy accumulate. Planets, stars, and galaxies are its natural arena. This contrast between universality and weakness is not accidental. It hints that gravity is woven into the structure of space-time itself, rather than added on as an interaction between particles. Observations across the solar system confirm this picture with remarkable accuracy. The orbit of Mercury shifts slightly over time in a way that Newtonian gravity cannot fully explain, yet general relativity predicts exactly. Signals sent past massive objects experience delays as space-time curves their paths. Binary pulsars, pairs of dense stellar remnants locked in close orbits, gradually lose energy in precise agreement with the emission of gravitational waves. These systems act as natural laboratories, testing gravity under extreme conditions. And still, something remains unresolved. General relativity treats space-time as smooth and continuous. Quantum theory tells us that at the smallest scales, nature is discrete and uncertain. When gravity compresses matter into extremely small regions, these descriptions collide. The equations produce infinities not because the universe contains literal infinities, but because the theory has been pushed beyond its domain of validity. This is not a minor technical issue. It appears inevitably wherever gravity becomes strongest. At the beginning of the universe, where densities were enormous. At the centers of black holes, where collapse seems unavoidable. In these regimes, the mathematical structure of space-time itself breaks apart. The geometry becomes ill-defined. Predictability is lost. Gravity, then, occupies a strange position in physics. It is our most successful theory at large scales, yet it resists integration with the quantum framework that governs everything else. Attempts to treat gravity like the other forces lead to contradictions and infinities that cannot be removed by known methods. The universe demands consistency, but gravity refuses to comply easily. These difficulties are not signs of failure. They are clues. They tell us that gravity is revealing something fundamental about space-time, information, and the limits of description. The places where the theory breaks are not random. They are precisely where gravity exerts its greatest influence. And it is in those regions where space-time curves toward its limits and horizons begin to form, that gravity starts to connect with ideas that once seemed unrelated. Concepts like boundaries, temperature, and disorder quietly enter the picture. To understand gravity fully, we are forced to follow it into these extreme solutions of the equations, where familiar intuition fades and deeper structure waits just beneath the surface. As gravity draws matter inward, something subtle happens to the notion of cause and effect. In everyday life, influences propagate outward. A sound spreads through air. A signal travels from sender to receiver. But in strong gravitational fields, the structure of space-time itself begins to tilt. Paths that once allowed escape bend inward. Futures narrow. Possibilities collapse. This is not metaphor. It is geometry. In sufficiently curved space-time, there exist boundaries beyond which events cannot influence the outside world. These boundaries arise naturally from the equations of general relativity. They do not require exotic matter or artificial conditions. They form whenever gravity becomes strong enough. Once crossed, all possible future paths lead deeper inward. Nothing needs to pull. The geometry alone is enough. What makes this unsettling is not merely that objects cannot escape, but that information cannot escape. Light, signals, and even the passage of time itself are affected. An observer far away never sees an object cross such a boundary. Instead, the object appears to slow, dim, and freeze. From the falling object's own perspective, nothing special happens at the boundary. These two descriptions are both correct, and they cannot be reconciled within classical gravity alone. This tension reveals a deeper issue. General relativity treats spacetime as smooth and continuous, but horizons introduce sharp divisions. They separate regions of knowledge. They define what can be observed and what cannot. In doing so, they force gravity to confront questions usually reserved for thermodynamics and information theory. Even before black holes were taken seriously as physical entities, these implications were already present. The equations did not merely describe motion. They encoded limits on observation, limits on prediction, limits on what can be known by any single observer. And yet, gravity offers no explanation for why these limits exist. It describes them with precision, but it does not explain their origin. It tells us how spacetime behaves near extreme curvature, but not why spacetime should have this behavior at all. The theory is silent on what spacetime is made of, or whether it is made of anything. This silence becomes impossible to ignore when gravity is combined with quantum theory. Quantum mechanics insists that information is preserved. Processes may be unpredictable, but they are reversible in principle. Nothing is ever truly lost. General relativity, when pushed to its extremes, seems to allow information to disappear behind boundaries forever. These two principles cannot both be correct in their current forms. This conflict does not appear in weak gravity. It does not affect falling apples or orbiting planets. It emerges only when gravity becomes strong enough to create horizons. In other words, the deepest problem with gravity is not revealed by motion, but by limits. Not by forces, but by boundaries. This is why black holes matter so profoundly. They are not exotic exceptions. They are the places where gravity is forced to reveal its full structure. They expose the edges of our theories. They turn abstract mathematical limits into physical questions. Gravity, when followed far enough, stops being only about motion and curvature. It begins to speak the language of entropy, temperature, and information. These ideas do not enter as metaphors. They enter as necessities, and once they appear, they cannot be removed. When the term black hole is used in everyday language, it often evokes the image of a cosmic object, something like a star or a planet, but darker and more extreme. This picture is understandable, yet it is misleading. In the language of physics, a black hole is not defined as a thing sitting in space. It is defined as a solution to equations. It is a specific way spacetime itself can be arranged when gravity dominates completely. General relativity does not predict black holes by naming them or describing their interiors. It predicts them by allowing certain exact solutions to its field equations. These solutions describe regions where spacetime curvature becomes so strong that ordinary intuition fails. Long before astronomers had evidence for their existence, these solutions were already present on paper, quietly implying that gravity, if left unchecked, leads to boundaries in spacetime. The simplest of these solutions was found by Carl Schwarzschild shortly after Einstein completed his theory. It describes the spacetime outside a perfectly spherical, non-rotating mass. What makes this solution remarkable is not the presence of a singularity at the center, but the appearance of a critical surface surrounding it. At a specific distance from the mass, the geometry of spacetime changes character. Paths that once allowed escape no longer do. This surface is what we now call an event horizon. The event horizon is not a physical surface made of matter. It has no texture, no thickness, and no locally detectable marker. An observer falling through it would feel nothing unusual at that moment. The laws of physics in their immediate surroundings would appear unchanged. And yet, once crossed, the future is constrained. All possible paths forward in time lead inward. Escape is no longer part of the geometry. This is what makes black holes so difficult to visualize. They are not objects embedded in space. They are regions where space and time themselves behave differently. The horizon is not a place where something happens. It is a boundary between what can influence the outside universe and what cannot. More realistic black holes are described by solutions that include rotation. Most astrophysical objects spin, and collapsing stars are no exception. The Kerr solution captures this behavior. In this geometry, spacetime is dragged along with the rotating mass. Directions mix. Orbits twist. The horizon remains, but it is no longer spherical. The structure of spacetime becomes richer and more complex, yet the defining feature remains the same. A boundary forms beyond which information cannot escape. For decades, these solutions were treated as mathematical curiosities. It was unclear whether nature would ever realize such extreme configurations. That uncertainty no longer exists. Observations of stars orbiting invisible massive centers, disks of hot gas emitting intense radiation, and gravitational waves from merging compact objects all point to the same conclusion. The universe does produce black holes, and yet, even with this evidence, it is crucial to remember what they are. Black holes are not exotic matter. They are not objects with mysterious internal substances. They are gravitational solutions. They are space-time arranged in a particular way. And it is precisely because they are solutions, not objects, that their properties lead so directly to deeper questions about gravity itself. What makes these solutions compelling is how little they depend on the details of what collapsed to form them. Once a black hole settles, its external spacetime is determined by only a few quantities: mass, rotation, electric charge. Everything else about the original star, its composition, its internal structure, even the complex processes that occurred during collapse, becomes irrelevant to the geometry outside the horizon. This simplicity is not an assumption. It is a consequence of the equations themselves. This feature is sometimes described as the loss of distinguishing information, but it is more precise to say that general relativity no longer allows that information to influence the outside world. The space-time geometry forgets. Not because information is destroyed, but because the theory provides no channel through which it can emerge. From the perspective of an external observer, vastly different initial states can lead to identical black holes. The equations compress complexity into geometry. This compression has observable consequences. Matter falling toward a black hole heats up, forming an accretion disk that radiates intensely before crossing the horizon. These disks emit X-rays and other high-energy radiation that can be detected across enormous distances. Their behavior matches predictions based on relativistic motion in curved spacetime. The energy released does not come from the black hole itself, but from matter losing gravitational energy as it spirals inward. In some systems, stars orbit unseen companions at tremendous speeds. By measuring these orbits, astronomers can infer the mass of the central object. In several cases, the mass is too large to be a neutron star and too compact to be anything other than a black hole. At the centers of galaxies, including our own, stars follow paths that reveal the presence of extremely massive and compact gravitational sources. The simplest explanation consistent with all observations is that these sources are supermassive black holes. The most direct confirmation came from gravitational waves. When two compact objects spiral together and merge, they disturb spacetime in a characteristic way. The signals detected from such events match precisely the waveforms predicted for black hole mergers. The final stage of these signals shows the newly formed black hole settling into a stable configuration, radiating away distortions until only a clean solution remains. The data align not with speculation, but with exact mathematical predictions. Perhaps the most striking evidence is visual. By observing the motion of hot gas near the event horizon, astronomers have reconstructed images of the shadow cast by a black hole against surrounding light. These images do not show the black hole itself, which emits nothing, but the outline of the region where spacetime bends light so strongly that it cannot escape. The shape and size of this shadow agree with general relativity to remarkable accuracy. All of this confirms that black holes are real features of our universe, but it also reinforces a deeper point. What we observe is not an object in the usual sense. We observe the behavior of spacetime around a region where gravity has taken full control. The defining feature is not the singularity, which remains hidden and theoretically problematic. The defining feature is the horizon, a boundary created by geometry alone. And once this boundary exists, something unexpected happens. The black hole begins to resemble a thermodynamic system. It behaves as though it has properties like temperature and entropy, not metaphorically, but mathematically. This resemblance is not added by hand. It emerges inevitably when the behavior of horizons is examined carefully. The appearance of thermodynamic behavior in black hole solutions is one of the most unexpected results in modern physics. Nothing in the original formulation of general relativity suggests that space-time geometry should be associated with heat or disorder. The theory contains no atoms of space-time, no microscopic constituents, no statistical ensembles. And yet, when horizons are present, quantities arise that behave exactly like thermodynamic variables. Consider what happens when matter falls into a black hole. From the outside, the horizon grows, its surface area increases. This growth is not arbitrary. There are precise mathematical theorems showing that, under very general conditions, the total area of event horizons can never decrease. No matter what processes occur outside, no matter how violent the merger or collapse, the horizon area after the process is always greater than or equal to what it was before. This behavior is strikingly similar to the second law of thermodynamics, which states that entropy never decreases in an isolated system. At first, this resemblance was thought to be a coincidence, a formal analogy with no physical content, but the analogy refused to go away. The equations lined up too precisely. Horizon area behaved like entropy in every essential way. This posed an immediate problem. If a black hole absorbs matter with entropy, and if the horizon area is not associated with any physical entropy of its own, then total entropy would appear to decrease when matter disappears behind the horizon. That would violate one of the most fundamental principles of physics. The only consistent resolution was that black holes themselves must carry entropy. This was a radical idea. Entropy counts microscopic configurations. It measures how many internal states correspond to the same macroscopic appearance. Assigning entropy to a black hole meant accepting that it has microscopic degrees of freedom, even though general relativity provides no description of them. The smooth geometry must be hiding something deeper. What made this conclusion unavoidable was its precision. The entropy of a black hole is not arbitrary. It is proportional to the area of its horizon, not its volume. This scaling is profoundly counterintuitive. In ordinary systems, entropy grows with volume. Here, it grows with surface area. The information content of a region appears to live on its boundary. This result does not depend on the details of the black hole. It applies to non-rotating and rotating solutions alike. It emerges from different theoretical approaches. It remains consistent across independent derivations. The implication is clear. Black holes are not simple sinks of matter and energy. They are thermodynamic systems defined by geometry. Once this is accepted, gravity can no longer be viewed as a purely geometric theory in the classical sense. The presence of entropy demands microscopic structure. It demands degrees of freedom. And yet, those degrees of freedom are nowhere to be found within space-time itself, as described by general relativity. This is where black holes stop being endpoints of collapse and start becoming guides. They expose a tension between smooth geometry and statistical behavior. They suggest that space-time, like matter, may emerge from something more fundamental. Gravity, when pushed to its extreme, does not merely curve space-time. It reveals its hidden thermodynamic character. When the idea first emerged that black holes might obey laws resembling thermodynamics, it was treated with deep skepticism. Thermodynamics is a theory about heat, work, and microscopic disorder. It applies to systems made of many constituents, atoms or molecules, whose collective behavior gives rise to temperature and entropy. General relativity, by contrast, describes spacetime as smooth and continuous. It contains no particles of geometry, no statistical ingredients, no obvious source of thermodynamic behavior. And yet, the mathematics pointed insistently in that direction. The connection begins not with speculation, but with precise results derived directly from the equations of gravity. In the early 1970s, physicists studying black hole solutions noticed that certain quantities obeyed relationships strikingly similar to the laws of thermodynamics. The surface gravity of a black hole behaved like temperature. The horizon area behaved like entropy. The mass played a role analogous to energy. These were not poetic comparisons. They were exact mathematical correspondences. The first of these relationships mirrors the conservation of energy. When matter falls into a black hole, the mass of the black hole increases. If the black hole rotates or carries electric charge, those quantities change as well. The variations are not independent. They are linked by an equation that resembles the first law of thermodynamics, relating changes in energy to changes in entropy and other parameters. This law emerges directly from the geometry of spacetime near the horizon. The second relationship concerns irreversibility. Under very general conditions, the total area of all event horizons in a closed system never decreases. Horizons can merge and grow. They can distort and settle, but they do not shrink. This result is known as the area theorem, and it is derived without invoking quantum mechanics or statistical assumptions. It follows purely from classical gravity, provided certain reasonable energy conditions are satisfied. The resemblance to the second law of thermodynamics is impossible to ignore. In thermodynamics, entropy never decreases in an isolated system. In gravity, horizon area never decreases. Both laws describe a preferred direction of evolution, a built-in arrow of time. This is remarkable because the fundamental equations of general relativity are time-symmetric. They do not distinguish past from future, and yet the presence of horizons introduces an irreversible behavior. At first, this parallel was treated cautiously. Many physicists assumed it was a formal coincidence, a mathematical curiosity with no physical meaning. After all, if black holes had no temperature, no radiation, and no internal structure, then their entropy could not be real. It would be a bookkeeping device, not a physical quantity. But this interpretation created contradictions. If a black hole absorbs matter carrying entropy, and if the black hole itself has no entropy, then total entropy outside the horizon decreases. That would violate the most robust principle in thermodynamics. To preserve consistency, the horizon itself must contribute entropy. The area cannot merely resemble entropy. It must be entropy. This conclusion did not arise from philosophy. It arose from the demand that physics remain self-consistent. Once accepted, it transformed the role of horizons entirely. They were no longer passive boundaries. They became active participants in thermodynamic accounting. Space-time geometry began to behave like a statistical system. This realization raised a profound question. If horizons have entropy, what microscopic degrees of freedom are being counted? General relativity provides no answer. It treats the horizon as smooth and featureless. Yet the thermodynamic behavior demands an underlying structure. Something unseen must be responsible. The mystery deepens when we ask why horizons behave this way at all. Thermodynamic laws usually arise because we choose to ignore microscopic details. We average over countless configurations we cannot track individually. Entropy measures that ignorance. But in gravity, there is no obvious collection of microscopic states to ignore. The horizon is defined globally, not locally. It is not something an observer can detect by crossing it. And yet it carries entropy as precisely as any physical system. One clue lies in the role of observers. Horizons do not exist for everyone. An observer far from a black hole sees a boundary beyond which signals never return. An observer falling freely does not encounter a barrier at the horizon. This observer dependence is crucial. Thermodynamics itself is tied to coarse graining, to what an observer can and cannot access. In gravity, the horizon defines a limit on information. It divides space-time into accessible and inaccessible regions. When information becomes inaccessible, entropy appears. This is not unique to black holes. Even in flat space-time, uniformly accelerating observers experience a horizon. They cannot receive signals from certain regions. Remarkably, such observers also detect a temperature. Empty space appears warm to them. This effect arises not from particles being created in the usual sense, but from the structure of space-time combined with the observer's motion. Horizons and temperature appear together. This insight reveals that thermodynamics is not an add-on to gravity. It is woven into the causal structure of space-time. Wherever horizons appear, thermodynamic behavior follows. The laws governing horizon area, surface gravity, and mass are not accidents. They reflect deep relationships between geometry, information, and observation. Yet classical gravity alone cannot complete the picture. In the classical theory, black holes do not radiate. Their temperature, if defined at all, would be zero. Without radiation, entropy would be a static quantity, never exchanged with the environment. True, thermodynamics requires temperature in the physical sense, not just formal analogy. It requires heat flow. This is where quantum theory becomes unavoidable. Quantum fields do not remain quiet near horizons. Even in vacuum, fluctuations are present. Near a horizon, these fluctuations are distorted by the geometry of spacetime. The separation between what an observer can see and what remains hidden becomes physically meaningful. Energy appears where none was expected. The realization that horizons must have temperature did not come from modifying gravity, but from applying quantum field theory to curved spacetime. When this is done carefully, the formal analogy becomes physical reality. Black holes are not cold. They emit radiation. Their entropy is not symbolic. It governs real exchanges of energy. At this point, the thermodynamics of horizons stops being a curiosity and becomes a requirement. Any theory that combines gravity and quantum mechanics must account for these effects. Horizons are no longer just geometric boundaries. They are thermodynamic objects with measurable consequences, even if those consequences are subtle and extremely difficult to observe directly. This realization carries a heavy implication. If black holes have temperature and entropy, then they must evolve. They must change. They cannot be eternal sinks. And if they evolve, then the fate of information becomes unavoidable. The final piece of the thermodynamic picture emerges when all these threads are brought together. Horizon area behaves like entropy. Surface gravity behaves like temperature. Quantum fields ensure that horizons are not inert. They interact. Energy flows. Once these facts are accepted simultaneously, black holes can no longer be treated as static solutions frozen in time. They become physical systems that obey the same statistical rules as everything else in nature. This shift is profound. Thermodynamics is not optional. It is one of the most reliable frameworks in all of physics. It applies to gases, solids, radiation, and information. Any system with entropy and temperature must obey its laws. Black holes are no exception. Their horizons encode disorder. Their geometry responds to energy exchange. And their evolution must respect the increase of total entropy. What makes this unsettling is how little general relativity has to say about the microscopic origin of these effects. The equations describe spacetime as smooth and continuous, down to arbitrarily small scales. There are no built-in units of area, no discrete elements, no underlying lattice. And yet, entropy demands counting. It demands structure. Something must be counted to produce such a precise and universal result. The scaling of entropy with area rather than volume sharpens the puzzle. In ordinary matter, entropy grows with the number of particles, which grows with volume. For black holes, entropy grows with the size of a boundary. This suggests that the fundamental degrees of freedom associated with gravity do not fill space the way matter does. They appear to reside on surfaces. The interior volume becomes secondary. This observation does not depend on speculative assumptions. It follows from consistency between gravity, quantum theory, and thermodynamics. If any one of these frameworks is abandoned, contradictions arise. If thermodynamics fails, the arrow of time collapses. If quantum mechanics fails, predictability is lost. If gravity fails, spacetime itself becomes meaningless. The only viable option is that they are all telling part of the same story. Horizons force these stories to intersect. They expose the limits of observation. They transform ignorance into entropy. They turn geometry into a thermodynamic quantity. And they do so in a way that is precise, universal, and unavoidable. By the end of this chapter, gravity no longer appears as a force or even purely as geometry. It begins to resemble a statistical phenomenon, emerging from deeper degrees of freedom that we do not yet understand. This does not explain gravity. It reframes the problem. Instead of asking how gravity acts, we are compelled to ask what spacetime is made of. Black holes do not answer that question, but they constrain the answer tightly. Any future theory of gravity must reproduce horizon thermodynamics exactly. It must explain why entropy scales with area. It must explain why temperature arises at boundaries. And it must do so without violating the principles that have already proven themselves across the universe. This is why the thermodynamics of horizons is not a side story. It is the spine of the mystery. Gravity, when examined where it is strongest, stops behaving like a classical field and starts behaving like an emergent system governed by information. Entropy is often misunderstood as a vague measure of disorder, but in physics, it has a precise meaning. It counts how many microscopic arrangements can give rise to the same macroscopic appearance. Two systems may look identical from the outside, yet one may hide vastly more internal possibilities than the other. Entropy measures that hidden richness. It is not a matter of interpretation. It is a physical quantity that can be calculated, compared, and conserved in specific ways. When entropy first entered the discussion of black holes, it did so reluctantly. The idea that a region of spacetime could possess entropy seemed almost contradictory. Spacetime, as described by general relativity, has no atoms. It has no molecules. It is a smooth geometric entity. And yet the logic was unavoidable. If black holes absorb matter that carries entropy, and if the horizon area always increases, then the horizon itself must account for that entropy. Otherwise, the second law of thermodynamics would be violated. This was not a matter of philosophical preference. It was a matter of consistency. The second law has never been observed to fail. It governs everything from chemical reactions to the evolution of stars. To abandon it in the presence of black holes would require overwhelming evidence. No such evidence exists. The simpler conclusion is that black holes possess entropy of their own. What makes this conclusion extraordinary is how that entropy scales. For ordinary systems, entropy grows with volume. Double the volume, and you roughly double the number of microscopic states. Black holes do not follow this rule. Their entropy is proportional to the area of the event horizon, not the interior volume, not the mass directly, the surface area. This relationship is exact. It does not depend on the type of black hole. It applies to non-rotating solutions and rotating ones alike. It holds regardless of how the black hole formed. The proportionality constant involves fundamental constants of nature, linking gravity, quantum theory, and thermodynamics in a single expression. This is not coincidence. Independent calculations using different methods all lead to the same result. One way to see this is through thought experiments involving information. Imagine lowering a container of matter toward a black hole. The matter carries entropy. If it crosses the horizon, that entropy disappears from the outside world. To preserve the second law, the black hole's entropy must increase by at least the same amount. Detailed analysis shows that the increase in horizon area precisely compensates for the lost entropy, provided the entropy is proportional to area. Another route arrives at the same conclusion by examining quantum fields near the horizon. Fluctuations pile up near the boundary, contributing degrees of freedom that scale with surface area rather than volume. Different approaches, starting from different assumptions, converge on the same answer. Black hole entropy is not a metaphor. It is a calculable physical quantity. This realization forces a dramatic shift in how gravity is understood. If spacetime can carry entropy, then it must have microscopic structure, even if that structure is hidden from direct observation. The smooth geometry described by general relativity cannot be fundamental. It must be an effective description, like temperature or pressure, emerging from something deeper. At this point, the question is no longer whether black hole entropy is real. It is. The question is what it is counting. And that question leads directly to the deepest unsolved problem in fundamental physics. The search for what black hole entropy counts has led physics into unfamiliar territory. In ordinary systems, entropy counts microscopic states of matter. Atoms vibrate, molecules rearrange, particles move in countless configurations. But a black hole, as described by classical gravity, has no such ingredients. Its exterior is defined entirely by a small set of parameters. Its interior is hidden, and its horizon is smooth. There is nothing obvious to count. This absence is the heart of the problem. Entropy is not optional. Its numerical value is enormous for astrophysical black holes. A black hole with the mass of the Sun has an entropy far exceeding that of ordinary matter with the same mass. This is not a small correction or a subtle effect. It dominates. Whatever degrees of freedom gravity is hiding, there are unimaginably many of them. One approach to understanding this comes from quantum field theory applied to curved spacetime. Near a horizon, quantum fields behave differently than they do in empty space. Modes of these fields become highly compressed near the boundary. The number of possible configurations grows rapidly as one approaches the horizon. When this contribution is calculated carefully, it produces an entropy that scales with area. The horizon acts like a reservoir of microscopic possibilities. Another approach comes from attempts to quantize gravity itself. In certain theoretical frameworks, black hole entropy can be reproduced by counting states that exist at or near the horizon. These calculations do not rely on hand-waving arguments. They produce the correct proportionality and the correct numerical coefficient. While these frameworks differ in their details, they agree on the central result. The entropy is real, and it is associated with the horizon. What is striking is that the interior volume of the black hole does not appear in the calculation. One might expect that a larger interior would hold more information. But the entropy does not care about volume. It cares only about the boundary. This suggests that the information describing a region of spacetime is encoded on its surface, not throughout its interior. The familiar intuition that information fills space breaks down in the presence of gravity. This conclusion is deeply unsettling because it runs against everything learned from ordinary physical systems. Yet it is forced upon us by consistency. If black hole entropy scaled with volume, the second law would fail in thought experiments involving collapse and absorption. Only area scaling preserves the fundamental principles of thermodynamics. At this stage, gravity begins to look less like a fundamental interaction and more like an emergent phenomenon. Temperature emerges from microscopic motion. Pressure emerges from particle collisions. Entropy emerges from counting states. Black hole entropy suggests that spacetime itself may emerge from deeper degrees of freedom that we do not yet see. These ideas do not replace general relativity. They sit beneath it. General relativity remains an extraordinarily accurate description of large-scale behavior. But like thermodynamics, it may be an effective theory, valid when we do not resolve the underlying microstructure. Black holes force this possibility into the open. They are not anomalies that break the laws of physics. They obey those laws with ruthless precision, and in doing so, they expose the limits of our current descriptions. Gravity, when pressed to its extremes, demands a deeper explanation, one that can account for entropy, information, and the hidden structure of spacetime itself. The implications of black hole entropy do not remain confined to black holes themselves. Once entropy is tied to spacetime geometry, it becomes impossible to treat gravity as a purely geometric phenomenon divorced from microscopic physics. The horizon is not just a boundary of no return. It is a ledger. It keeps track. It accounts for information that would otherwise appear lost. What makes this unavoidable is the precision of the entropy formula. It is not approximate. It is not adjustable. It contains fundamental constants that belong to different areas of physics. Gravity, quantum theory, and thermodynamics all appear together, multiplied in a way that leaves no freedom to reinterpret the result. This convergence is rare in physics. When it occurs, it usually signals something deep and universal. The entropy associated with a black hole is enormous. For a stellar mass black hole, it exceeds the entropy of ordinary matter by many orders of magnitude. This tells us that gravitational systems are capable of storing far more information than systems made of particles alone. Gravity is not merely a background influence. It is an information-carrying structure. This realization changes how we think about collapse. When matter falls inward and a horizon forms, information does not vanish in a trivial way. It is redistributed. The exterior description becomes simpler, but the underlying accounting becomes richer. The horizon grows, and with it grows the entropy. The second law is preserved, but only because gravity itself participates in thermodynamics. At this point, a sharp tension appears. If black holes have entropy, then they should also have temperature, and if they have temperature, then they must exchange energy with their surroundings. Classical general relativity forbids this. Nothing escapes. The horizon is absolute. Yet thermodynamics insists that systems with temperature cannot remain isolated forever. This tension cannot be resolved within classical gravity alone. It requires quantum mechanics. The moment quantum effects are taken seriously near horizons, the picture changes. Boundaries that were once perfect become slightly permeable. Energy begins to leak, not as matter escaping, but as radiation emerging from the quantum structure of spacetime itself. The existence of black hole entropy therefore points directly toward an even more unsettling conclusion. Black holes cannot be eternal. They must evolve. They must lose mass. And if they lose mass, then whatever information they store must eventually be accounted for. This realization does not yet tell us how information escapes. It tells us that it must. The entropy cannot simply disappear. The laws that demanded its existence also demand its conservation in a broader sense. Black hole entropy is real. Its implications are unavoidable, and it carries us directly to the edge of one of the deepest conflicts in modern physics. A conflict not between theories, but between principles. The principle that information is never lost, and the classical picture of horizons as absolute boundaries. Resolving that conflict will require confronting the quantum behavior of gravity itself. And that confrontation begins with the phenomenon that turns black holes from silent sinks into active participants in the universe. For a long time, black holes were thought to be perfectly black. According to classical general relativity, nothing escapes once it crosses the horizon. No matter, no light, no signal of any kind. The boundary is absolute. From the outside, a black hole can only grow. It can absorb, it can merge, but it cannot lose energy. This picture is internally consistent, but it sits uneasily beside thermodynamics. A system with entropy and temperature cannot remain forever isolated. Temperature is not a label. It is a measure of how energy is exchanged. If black holes truly possess entropy, then assigning them a temperature without allowing any radiation would empty the concept of meaning. Something had to give. The resolution came from combining gravity with quantum field theory in curved spacetime. When quantum fields are examined near an event horizon, the vacuum is no longer simple. In quantum theory, empty space is not empty. It is filled with fluctuations. Pairs of excitations constantly appear and disappear, borrowing energy briefly before annihilating. In flat spacetime, these processes leave no lasting trace. Near a horizon, the situation changes. The strong curvature of spacetime alters how these fluctuations are perceived by distant observers. Modes of quantum fields that would normally cancel out become separated by the presence of the horizon. One part of a fluctuation can fall inward, while the other escapes. To an external observer, this appears as radiation emerging from the vicinity of the black hole. This radiation is not emitted from the interior. Nothing escapes from inside the horizon. The effect arises entirely from the geometry of spacetime outside it. The black hole behaves as though it has a temperature, emitting particles with a characteristic spectrum. This temperature depends on the mass of the black hole. The larger the mass, the lower the temperature. For astrophysical black holes, the temperature is extraordinarily small. This is why Hawking radiation has not been observed directly. For a black hole with the mass of the Sun, the temperature is far below the background radiation that fills the universe. Any emission is completely overwhelmed. The effect is real, but it is subtle. Its importance lies not in immediate observability, but in consistency. Once radiation exists, energy conservation demands a consequence. The energy carried away must come from the black hole itself. As radiation escapes, the black hole loses mass. Very slowly, over immense spans of time, it shrinks. Given enough time, it will evaporate entirely. The timescales involved are vast. A stellar mass black hole would take far longer than the current age of the universe to evaporate. The process is irrelevant for stars and galaxies, but it is crucial for principles. Hawking radiation transforms black holes from eternal objects into evolving systems. This result is accepted not because it has been measured, but because it is robust. Independent derivations, using different methods, arrive at the same conclusion. The effect does not rely on speculative physics. It uses quantum field theory and general relativity, both of which are exceptionally well tested in their domains. And once accepted, it forces a profound question. If black holes evaporate, and if they once absorbed matter carrying information, then what happens to that information as the black hole disappears? The existence of Hawking radiation changes the logical structure of black holes completely. A black hole is no longer a one-way sink that only grows. It is a system with a life cycle. It forms, it evolves, and over immense stretches of time, it fades away. This alone would be remarkable, but the deeper consequence lies in what this evaporation implies for information. In quantum mechanics, information is not a vague concept. It is built into the mathematics. The evolution of a quantum system is governed by rules that preserve information exactly. States may change, they may spread out, they may become entangled with their surroundings, but they do not disappear. If information were truly destroyed, the predictive structure of quantum theory would collapse. Probabilities would no longer add up consistently. Cause and effect would lose meaning. When matter falls into a black hole, it carries information. Not just about its composition, but about its quantum state. In classical gravity, that information crosses the horizon and is gone forever from the outside world. But Hawking radiation complicates this picture. The radiation appears thermal. It depends only on the mass and rotation of the black hole. It does not seem to carry detailed information about what fell in. If the black hole evaporates completely, and if the radiation is truly featureless, then the information would be lost. This is not a philosophical discomfort. It is a direct contradiction between two pillars of modern physics. General relativity allows horizons that hide information permanently. quantum mechanics forbids information loss. Hawking radiation forces these principles into direct conflict. At first, it was tempting to accept that quantum mechanics might fail in the presence of gravity. Perhaps black holes really do destroy information. But this idea leads to serious problems. If information can be destroyed in one process, it becomes difficult to prevent its destruction in others. Quantum theory would lose its foundation. Few physicists are willing to accept this. Another possibility is that the radiation is not truly thermal. Perhaps subtle correlations exist between the emitted particles. Individually, the radiation looks random. Collectively, over the full lifetime of the black hole, the information might be encoded in delicate patterns. These patterns would be unimaginably difficult to detect, but in principle, they could preserve unitarity. The challenge is that semi-classical calculations appear to forbid this. When Hawking radiation is derived using quantum fields on a classical spacetime background, the outgoing radiation is entangled with degrees of freedom that fall behind the horizon. As evaporation proceeds, this entanglement grows. Eventually, the amount of entanglement exceeds what the remaining black hole can support. Something must give. This is where the problem sharpens. The conflict does not arise at the beginning of evaporation. It arises halfway through, when the black hole has lost a significant fraction of its mass. At that point, simple pictures fail. Either information escapes, or the interior description breaks down, or quantum mechanics must be modified. None of these options is comfortable. Each implies a profound change in our understanding of spacetime, information, or both, and yet the problem cannot be ignored. Hawking radiation is not an optional detail. It is required by consistency between gravity and quantum theory. What began as a subtle quantum effect near horizons now stands as a central challenge. Black holes are no longer just tests of strong gravity. They are tests of the foundations of physics. The question is no longer whether black holes evaporate. The question is how the universe keeps track of what falls in. The full weight of the problem becomes clear only when evaporation is followed to its logical end. If a black hole begins in a well-defined quantum state and evaporates completely into radiation that carries no memory of that state, then the final state of the universe cannot be predicted from the initial one. Different beginnings lead to the same ending. This violates unitarity, the principle that underlies all of quantum mechanics. This is not a small inconsistency that can be repaired with a minor adjustment. Unitarity is what allows probabilities to remain meaningful. It ensures that information is conserved even when systems become complex and entangled. Without it, quantum theory loses its predictive power. Processes would not be reversible even in principle. The mathematical framework would fracture. For this reason, most physicists believe that information is not destroyed by black holes. The challenge is explaining how it survives. Hawking radiation, in its simplest form, appears too random to carry information, but appearances can be deceptive. In quantum systems, information is often hidden in correlations rather than in individual outcomes. Two particles can look random on their own, yet together encode precise information. One possibility is that the radiation emitted at late times is subtly correlated with radiation emitted earlier. Over the full lifetime of the black hole, these correlations could encode everything that fell in. From the outside, the process would look thermal at first, but gradually become more structured. Information would leak out slowly, spread thinly across vast amounts of radiation. Another possibility is that the interior description itself fails before complete evaporation. Perhaps spacetime inside the horizon does not exist in the way classical gravity suggests. Perhaps the smooth geometry breaks down and is replaced by something fundamentally different. In that case, the apparent loss of information would be an artifact of using the wrong description. What makes the problem so difficult is that it cannot be resolved using only semi-classical tools. Treating spacetime as classical while quantizing matter works well in many situations, but it reaches its limit here. The evaporation process probes exactly the regime where quantum gravity effects must become important. Without a complete theory of quantum gravity, The final answer remains out of reach. Yet this uncertainty is productive. It has narrowed the range of possibilities dramatically. Any acceptable resolution must preserve quantum mechanics. It must reproduce Hawking radiation at early times. It must respect black hole thermodynamics. And it must explain how information escapes without violating causality or locality in an obvious way. Black holes, once thought to be simple endpoints of collapse, have become laboratories for the deepest questions in physics. They force gravity, quantum theory, and thermodynamics into direct confrontation. They expose contradictions that cannot be ignored. And in doing so, they guide us toward new principles that must underlie spacetime itself. The consequences of Hawking radiation are therefore not limited to black holes. They reshape our understanding of what gravity is and what it must become. The problem of information is not a puzzle to be solved later. It is a signpost. It points toward a deeper description of the universe, one in which spacetime, entropy, and information are inseparable. The information problem is often described as a paradox, but this word can be misleading. A paradox suggests a trick of logic or a confusion in language. What appears in black holes is neither. It is a direct conflict between principles that have each been tested with extraordinary success. On one side stands quantum mechanics, which insists that information is never destroyed. On the other stands classical gravity, which allows information to disappear behind horizons forever. Hawking radiation forces these two principles to confront each other without compromise. To understand why this matters, it is necessary to be precise about what information means in physics. Information is not memory or meaning. It is not data in the everyday sense. In quantum theory, information refers to the complete specification of a system's state. If that specification is lost, then future predictions become impossible even in principle. The theory stops being deterministic in its own probabilistic way. Quantum mechanics is built on unitary evolution. This means that the evolution of a closed system preserves information exactly. States may become complicated. They may spread across many degrees of freedom. They may become entangled with their environment, but they never collapse into something less than they were. The past is always encoded in the present, even if it is practically inaccessible. This principle has been confirmed repeatedly. Quantum systems behave reversibly at the fundamental level. Apparent irreversibility arises only when information is dispersed into correlations we choose not to track. Thermodynamic entropy increases, but microscopic information remains intact. This distinction is essential. It allows thermodynamics and quantum mechanics to coexist without contradiction. Black holes threaten this balance. When matter falls behind a horizon, its information becomes inaccessible to outside observers. In classical gravity, that inaccessibility is permanent. Hawking radiation appears to be thermal, carrying no detailed imprint of what fell in. If the black hole evaporates completely, the information seems to vanish from the universe altogether. This would be different from ordinary thermodynamic processes. When a hot object cools, its radiation carries information about its internal state, even if that information is highly scrambled. In principle, it can be recovered. Black hole evaporation, as originally described, offers no such recovery. The final radiation state looks the same regardless of how the black hole formed. If this were true, quantum mechanics would fail in a fundamental way. The evolution from an initial pure state to a final mixed state would break unitarity. The future would no longer encode the past. Physics would lose its internal consistency. This is why the information problem cannot be dismissed. It is not about interpretation. It is about whether the rules of quantum theory survive contact with gravity. The problem does not arise because black holes are exotic. It arises because they obey the laws of physics too well. They force those laws into a regime where their compatibility is no longer guaranteed. Several attempts have been made to soften the problem without abandoning core principles, but each encounters serious obstacles. One idea is that information remains inside the black hole until the very end, when it is released in a final burst. In this picture, the evaporation proceeds as Hawking described, producing nearly thermal radiation, while the information stays hidden behind the horizon. Only at the final moment, when the black hole becomes extremely small, does the information escape. This proposal faces immediate difficulties. By the time the black hole has evaporated to a tiny remnant, there is no longer enough energy available to encode the vast amount of information that originally fell in. The entropy of the radiation already emitted is enormous. A small remaining object cannot store what has been lost. To make this work, one must assume the existence of stable remnants with unlimited internal states. Such objects would create severe problems elsewhere in physics, including uncontrolled production in ordinary processes. Another idea is that information is destroyed and quantum mechanics must be modified. This option has been explored seriously, but it comes at a high price. If information can be lost in black holes, it becomes difficult to prevent information loss in other processes. The structure of quantum theory relies on unitarity to remain predictive. Once that structure is weakened, probabilities no longer behave consistently. Small violations would tend to grow, undermining the theory far beyond gravity. A more subtle possibility is that information never truly enters the black hole interior in the way classical gravity suggests. Instead, it might be stored near the horizon, spread across microscopic degrees of freedom associated with the boundary itself. From the outside, matter appears to fall inward. From a deeper description, the information might be absorbed and encoded on the horizon. As the black hole radiates, this information could gradually be returned to the universe. This idea aligns naturally with the area scaling of black hole entropy. If the entropy counts degrees of freedom associated with the horizon, then the horizon may function as a kind of information buffer. The interior description would then be an effective one, valid only at large scales. At a fundamental level, there may be no separate interior region capable of hiding information permanently. What makes this proposal attractive is that it preserves unitarity without requiring exotic remnants or modifications of quantum mechanics. But it introduces a new tension. If information is stored at the horizon and released through radiation, then the classical picture of a smooth horizon must break down. Something must replace it. The horizon cannot be entirely featureless. This leads to difficult questions about locality and causality. In ordinary physics, information cannot be duplicated. Yet if information appears to be both inside the black hole and encoded in outgoing radiation, duplication seems unavoidable. Resolving this requires a careful reconsideration of what different observers can access and how their descriptions relate. These challenges show that the information problem is not a single puzzle with a single missing piece. It is a pressure test. It probes the consistency of our deepest assumptions about space-time and quantum theory. Any resolution must explain why semi-classical calculations appear to lose information while the underlying theory does not. The problem forces us to confront a possibility that would have seemed implausible before black holes were taken seriously. Space-time itself may not be fundamental. The interior of a black hole may not be an independent region in the way classical geometry suggests. The smooth fabric of space-time may be an approximation that fails precisely where information accounting becomes critical. The deeper one follows the information problem, the clearer it becomes that it is not confined to black holes alone. It reflects a more general tension between how space-time is described and how information behaves. Classical gravity assumes that space-time is a fixed arena, smooth and continuous, within which events occur. Quantum theory treats information as fundamental and indestructible. When these two views are forced together, something must change. One of the most important lessons of the information problem is that horizons are not passive features. They actively participate in the bookkeeping of information. What appears lost to one observer may remain encoded in a form that is inaccessible but not destroyed. This distinction between loss and inaccessibility is subtle, yet it is essential. Thermodynamic entropy increases when information becomes dispersed, not when it ceases to exist. In black holes, dispersion takes an extreme form. Information is spread across correlations between the radiation, the horizon, and whatever microscopic structure underlies spacetime. Recovering it would require access to degrees of freedom that no observer can fully control. From a practical standpoint, the information is lost. From a fundamental standpoint, it may still be present. This perspective reframes the problem. Instead of asking where information goes, the more appropriate question becomes how spacetime encodes it. The classical notion of an interior region may be an emergent description that breaks down when pushed too far. The true degrees of freedom might live elsewhere, perhaps on boundaries rather than in volumes. What is striking is how tightly constrained the resolution must be. Any acceptable explanation must reproduce Hawking radiation at early times. It must preserve the second law of thermodynamics. It must respect causality for observers who fall freely. And it must preserve unitarity for the universe as a whole. These requirements leave little room for arbitrary speculation. Black holes therefore serve as consistency tests for our theories. They do not allow us to hide contradictions behind approximations. They amplify small inconsistencies until they become unavoidable. In doing so, they guide us toward a more complete understanding of gravity, not by offering answers, but by eliminating false paths. The information problem remains unresolved, but it is no longer mysterious in the way it once was. Its structure is clear, its stakes are understood, and its implications extend far beyond black holes. They reach into the foundations of spacetime itself. Whatever the ultimate theory of gravity may be, it must explain why information appears to be lost and why it is not. It must reconcile the smooth geometry we observe with the precise accounting demanded by quantum theory. And it must do so in a way that makes horizons, entropy, and information parts of a single coherent framework. Black holes have forced this issue into the open. They have shown that gravity cannot be understood in isolation. It must be understood as part of a larger structure in which geometry, thermodynamics, and information are inseparably linked. The idea that information might not reside where we expect it to began as a response to a very specific problem. Black holes seemed capable of hiding vast amounts of information behind horizons, yet their entropy scaled with surface area, not volume. This was not a small detail. It was a radical clue. It suggested that the information content of a region of space is determined not by what fills it, but by what surrounds it. This insight led to a proposal that initially sounded implausible. Perhaps all the information contained within a volume of space can be represented on its boundary, not metaphorically, literally. In this view, the interior description is not fundamental. It is an effective reconstruction from degrees of freedom that live on a lower dimensional surface. This idea became known as the holographic principle. The name is inspired by holograms, where a two-dimensional surface encodes a three-dimensional image. But the principle itself is not an analogy. It is a statement about information bounds. It claims that the maximum amount of information that can be stored in a region scales with the area of its boundary, measured in fundamental units, not with its volume. The origin of this principle lies directly in black hole thermodynamics. If black hole entropy represents the maximum entropy a region of space can contain, then any attempt to pack more information into a region would cause it to collapse into a black hole. The horizon area would then set an absolute limit. This limit does not depend on the nature of the matter involved. It is imposed by gravity itself. What makes this compelling is its universality. The bound applies to all physical systems, not just black holes. Gravity enforces an information ceiling. No region of space can contain more information than a black hole of the same size. This is not a conjecture about technology. It is a statement about physical law. At first, the holographic principle was treated cautiously. It was unclear whether it was merely a bookkeeping tool or a deep statement about reality. But over time, concrete realizations emerged. In certain theoretical models, gravitational physics in a higher dimensional spacetime is exactly equivalent to a non-gravitational quantum theory defined on a lower dimensional boundary. Every process in the bulk has a precise counterpart on the boundary. Information is never lost. It is simply represented differently. These models do not describe our universe directly. They exist in idealized settings with special symmetries. But they demonstrate something crucial. Holography is not vague philosophy. It is mathematically precise. It preserves unitarity. It reproduces black hole entropy. And it resolves the information problem within its domain. At the same time, holography does not claim that space is an illusion or that the universe is literally flat. It does not say that reality is a projection. It says that the fundamental description of a gravitational system may be encoded in a different set of variables than those we use classically. Geometry may emerge from information rather than the other way around. This shift in perspective changes how gravity itself is viewed. If space-time geometry can be reconstructed from quantum degrees of freedom on a boundary, then gravity may not be fundamental. It may be an emergent phenomenon arising from the collective behavior of microscopic information. The holographic principle does not prove this, but it makes it plausible in a way that black holes alone could not. It provides a framework in which gravity, entropy, and information coexist without contradiction. And yet, this raises an even deeper question. If gravity emerges from information, then what determines the dynamics of space-time? What governs curvature? What fixes the equations that Einstein wrote down? Surprisingly, the answer may once again involve thermodynamics. The possibility that gravity might emerge from information rather than stand alongside it changes the nature of the question entirely. Instead of asking how space-time bends in response to matter, we are invited to ask why space-time exists at all. In holographic frameworks, space-time geometry is not assumed at the start. It is reconstructed. Distances, curvature, and even time itself arise from patterns of quantum entanglement in a deeper theory. One of the most striking aspects of these models is how naturally black hole entropy is explained. The boundary description contains a vast number of quantum degrees of freedom. When these degrees of freedom are counted, they reproduce the precise entropy associated with black hole horizons in the bulk description. Nothing needs to be added by hand. The area scaling emerges automatically. What looked mysterious from the gravitational side becomes ordinary from the informational side. In this picture, the interior of a black hole is not a separate region storing information independently. It is a derived concept. The fundamental description lives on the boundary, where information is never lost. The apparent disappearance of information behind a horizon is a feature of the bulk description, not of the underlying theory. This explains why semi-classical gravity seems to lose information while the full theory does not. What makes holography powerful is not that it solves every problem, but that it resolves the information problem in settings where it can be applied precisely. It shows that gravity and quantum mechanics are not incompatible in principle. They can coexist within a single consistent framework. The contradictions arise only when gravity is treated as fundamental and spacetime is assumed to be primary. At the same time, holography has clear limits. The best understood examples rely on highly symmetric spacetimes that differ significantly from our own universe. They require specific boundary conditions and mathematical structures that may not exist in nature as we observe it. This means holography is not a finished theory of reality. It is a guide, a proof of possibility. Still, its implications are difficult to ignore. If spacetime can emerge from entanglement, then the smooth geometry we experience may be a large-scale approximation, like temperature or pressure. At small scales, the true description may involve only quantum states and their correlations. Geometry would then be a convenient language for describing collective behavior, not a fundamental ingredient. This perspective also reframes the role of horizons. In holographic descriptions, horizons correspond to limits on entanglement. They mark where information becomes scrambled beyond local recovery. Thermodynamic behavior arises not because space-time is hot, but because information is distributed in ways that mimic heat when coarse-grained. Gravity, from this viewpoint, begins to resemble a macroscopic phenomenon. It is not added to the universe. It emerges from how information is organized. This does not diminish its reality. Temperature is real, pressure is real, yet both emerge from microscopic motion. Gravity may be similar, but emergence alone does not explain dynamics. Even if space-time arises from information, something must govern how that information evolves. Something must determine why geometry responds to energy in exactly the way Einstein described. And remarkably, when these questions are pursued carefully, thermodynamics appears once again. The final and most surprising development comes when gravity itself is derived from thermodynamic principles. This idea did not arise from holography directly, but from examining the behavior of horizons in space-time. When local patches of horizons are treated as thermodynamic systems, the equations governing space-time geometry emerge naturally. The starting point is deceptively simple. Assume that entropy is proportional to horizon area. Assume that energy flow across a horizon is related to heat. And assume that the laws of thermodynamics apply locally, not just globally. With these ingredients, one can derive the equations that describe how space-time curves in response to energy and momentum. The result is not an approximation, it is Einstein's equations themselves. This derivation does not claim that gravity is literally heat. It does not say that space-time is made of molecules in the usual sense. What it shows is that the geometric description of gravity is consistent with a deeper thermodynamic structure. The equations of general relativity can be seen as equations of state, relating energy, entropy, and geometry. This perspective is powerful because it reverses the usual logic. Instead of starting with space-time and deriving thermodynamics, it starts with thermodynamics and derives space-time. Geometry becomes a macroscopic consequence of microscopic information dynamics. Gravity is no longer fundamental, it is emergent. But this conclusion must be handled with care. Deriving Einstein's equations from thermodynamic assumptions does not prove that gravity is nothing but thermodynamics. It shows that the equations are compatible with such an interpretation. It shows that gravity can be understood as emergent, not that it must be. What remains unresolved is the nature of the microscopic degrees of freedom. The thermodynamic derivations do not identify them. They assume their existence. Holography provides candidates in certain settings, but a complete description remains elusive. This is where caution is essential. Many speculative models attempt to go further, claiming that gravity is an illusion or that space-time is not real. Such claims go beyond what the mathematics supports. The evidence tells us that gravity behaves like an emergent phenomenon in certain respects. It does not tell us that space-time is unreal. What can be said with confidence is that black holes and horizons have revealed a deep unity between gravity, thermodynamics, and information. These are not separate domains. They are different aspects of the same underlying structure. Ignoring any one of them leads to contradictions. The holographic principle and thermodynamic gravity do not provide final answers. They provide constraints. They tell us what any future theory must reproduce. It must explain why entropy scales with area. It must preserve information. It must reproduce Einstein's equations at large scales. And it must do so without introducing inconsistencies. Gravity, when followed to its logical extremes, stops being a standalone force and becomes part of a broader framework. One where geometry emerges from information and thermodynamics guides dynamics. Black holes are not exceptions to this framework. They are its most revealing examples. By the time gravity is examined through the lenses of black holes, entropy, and information, it no longer appears as a simple force or even solely as geometry. It begins to resemble a thermodynamic phenomenon, one governed by principles that emerge when microscopic details are averaged over. This does not mean gravity is reduced to heat or motion. It means that the equations describing spacetime may reflect deeper statistical behavior. The connection between gravity and thermodynamics is not limited to black holes. Horizons appear in many contexts. Any observer undergoing constant acceleration experiences a boundary beyond which signals cannot reach them. For that observer, empty space is not empty. It possesses a temperature. This effect arises even in flat spacetime, without curvature, showing that thermodynamic behavior is tied to horizons themselves, not only to gravitational collapse. This observation suggests that horizons are the key. They divide spacetime into regions of access and inaccessibility. Whenever such a division exists, entropy can be defined. Temperature follows. Energy flow acquires thermodynamic meaning. Gravity, in this view, is intimately connected to the existence of these boundaries. What is remarkable is that this connection can be made locally. One does not need a global black hole or a cosmic horizon. Small patches of spacetime can behave thermodynamically when viewed from the right perspective. When energy crosses a local horizon, it can be treated as heat. When entropy changes, spacetime responds by curving. This local thermodynamic response reproduces the familiar equations of gravity. This does not require new particles or forces. It relies on the assumption that entropy is proportional to area and that information is finite. These assumptions are already enforced by black hole physics. Once accepted, gravity emerges as the macroscopic behavior of spacetime responding to information flow. Still, caution is necessary. Thermodynamics describes how systems behave without specifying their microscopic details. Knowing that gravity has a thermodynamic description does not tell us what spacetime is made of. It tells us that spacetime behaves like a system with hidden degrees of freedom. The nature of those degrees of freedom remains unknown. What is gained from this perspective is clarity about limits. Gravity is not arbitrary. Its equations are constrained by thermodynamic consistency. Any modification to gravity must preserve entropy bounds and information conservation. These constraints are powerful. They narrow the space of possible theories. As gravity becomes stronger, thermodynamic effects become unavoidable. Horizons form. Entropy grows. Information becomes inaccessible. These features are not peculiarities of black holes. They are manifestations of a deeper structure governing spacetime itself. In this light, gravity appears less like a fundamental interaction and more like a large-scale description, emerging from microscopic laws that have yet to be fully uncovered. The universe, at its deepest level, may be governed by information, with spacetime and gravity arising as effective concepts. The thermodynamic perspective on gravity reshapes how we interpret Einstein's equations. In their usual form, these equations appear as fundamental laws, relating curvature to energy and momentum. From a thermodynamic viewpoint, they take on a different role. They become relationships that describe how spacetime responds when information and energy are redistributed. Curvature is no longer the cause, it is the response. This shift helps explain why gravity is universal. All forms of energy contribute because all forms of energy carry information. When energy moves, information moves. Horizons respond to that movement by adjusting their entropy. Spacetime curves to maintain consistency. Gravity does not need to distinguish between particles or forces. It responds only to the presence of energy and the flow of information. This also sheds light on why gravity is so weak at small scales. Thermodynamic laws emerge only when many degrees of freedom are involved. Temperature is meaningless for a single molecule. Pressure does not apply to one particle. Gravity may be similar. At microscopic scales, spacetime's underlying structure does not manifest as curvature. Only when enormous numbers of degrees of freedom act collectively does gravity emerge as a noticeable influence. Seen this way, the weakness of gravity is not a mystery. It is a signature of emergence. Strong interactions dominate at small scales, because they act directly on particles. Gravity dominates at large scales because it reflects collective behavior of spacetime itself. The thermodynamic interpretation also clarifies why gravity resists quantization. One does not quantize temperature or pressure directly. They arise from quantized constituents, but they are not themselves fundamental variables. Attempts to quantize gravity as if it were a basic force may be misguided. The true quantum theory may underlie spacetime, not describe it directly. This does not mean quantum gravity is unnecessary. It means its form may be very different from what intuition suggests. Instead of quantizing curvature, the correct approach may be to identify the microscopic degrees of freedom whose collective behavior produces geometry. Gravity would then appear automatically in the appropriate limit. These ideas remain incomplete. They rely on assumptions motivated by black hole physics and horizon thermodynamics. They have not yet been derived from a single underlying theory, but their consistency across many independent lines of reasoning gives them weight. Perhaps the most important implication is philosophical, but grounded in physics. Gravity may not be something the universe has. It may be something the universe does when information is arranged in certain ways. Spacetime may not be the stage on which physics plays out. It may be a consequence of deeper rules governing information and correlation. At the same time, this perspective does not diminish the reality of gravity. Emergent phenomena are no less real than fundamental ones. Temperature can melt ice, pressure can crush steel. Gravity shapes galaxies and governs the fate of stars. Its emergent nature, if confirmed, would explain its universality and its stubborn resistance to unification. These insights do not solve the problem of gravity. They reframe it. Instead of searching for a force to quantize, we are guided toward understanding the statistical origin of spacetime itself. Black holes, horizons, and entropy have forced this rethinking. They have revealed that gravity sits at the intersection of geometry, thermodynamics, and information. The final piece of this picture emerges when the limits of the thermodynamic interpretation are made explicit. Gravity behaves like an emergent phenomenon in many respects, but this does not mean it can be reduced to a single principle or equation. Thermodynamics constrains behavior. It does not specify microscopic details. In the same way, horizon thermodynamics constrains spacetime without revealing its underlying structure. What becomes clear is that gravity occupies a unique position among physical theories. It is not easily categorized as fundamental or emergent in the usual sense. It governs spacetime itself, yet its behavior suggests it arises from something deeper. It obeys geometric laws, yet those laws can be derived from information-theoretic assumptions. This dual character is not a flaw. It is a clue. Black holes have been essential in revealing this. They push gravity to its limits and expose its hidden layers. Without them, the connection between entropy and geometry might never have been discovered. Without horizons, the role of information might have remained invisible. Gravity would appear complete, even though it was not. The thermodynamic viewpoint also provides a powerful filter for speculation. Many proposed modifications of gravity fail immediately because they violate entropy bounds or information conservation. The second law of thermodynamics, when extended to horizons, becomes a guiding principle. Any viable theory of gravity must respect it. This narrows the field dramatically. At the same time, thermodynamics alone cannot determine everything. It does not tell us what spacetime is made of. It does not tell us how quantum degrees of freedom arrange themselves to produce geometry. It does not tell us why our universe has the specific properties it does. These questions remain open. What we gain instead is a clearer map of what gravity cannot be. It cannot be purely classical at all scales. It cannot ignore information. It cannot be independent of quantum principles. Any attempt to describe gravity without accounting for entropy and horizons will inevitably run into contradictions. In this sense, gravity is not hiding the truth. It is pointing toward it. The truth lies not in a single equation or model, but in the recognition that spacetime, information, and thermodynamics are inseparable. Black holes did not introduce these ideas, they revealed them. By the end of this chapter, gravity stands transformed, not explained, but reframed. It is no longer just the curvature of spacetime. It is the macroscopic expression of microscopic information dynamics. Whether this picture is complete remains unknown, but it has proven robust, consistent, and deeply suggestive. Gravity, once thought to be the simplest of forces, has become the most subtle. And that subtlety is not an obstacle. It is the path forward. After following gravity through black holes, entropy, information, and thermodynamics, it becomes necessary to pause and take stock. Not to draw conclusions prematurely, but to separate what is firmly established from what remains uncertain. In a subject as deep as gravity, clarity comes not from answers, but from knowing exactly where understanding ends. What we know is substantial. General relativity describes gravity with extraordinary accuracy across a vast range of conditions. Its predictions have been confirmed in the solar system, in binary star systems, and through the direct detection of gravitational waves. Space-time curvature is not a mathematical abstraction. It is a measurable physical effect that shapes the motion of matter, light, and time itself. We also know that black holes exist. They are not theoretical curiosities. They form from stellar collapse. They merge. They influence their surroundings. Their properties match the solutions of Einstein's equations with remarkable precision. Horizons are real features of spacetime, even though they cannot be detected locally by falling observers. We know that black holes obey laws that mirror thermodynamics. Horizon area behaves like entropy. Surface gravity behaves like temperature. These relationships are not metaphors. They are precise, universal, and unavoidable. They hold across different types of black holes and emerge from independent lines of reasoning. We know that quantum effects near horizons produce radiation. Hawking radiation follows inevitably from combining quantum field theory with curved spacetime. Although it has not been observed directly, it is accepted because it is theoretically robust and consistent with everything else we know. Black holes are not eternal. They evolve. We also know that information plays a central role. Quantum mechanics demands that information is preserved. Thermodynamics demands that entropy accounting remains consistent. Black holes force these demands into tension, revealing the limits of semi-classical descriptions. What we do not know is just as important. We do not know the microscopic origin of black hole entropy. We do not know what degrees of freedom spacetime is made of, or whether spacetime itself is fundamental. We do not know how information is encoded, stored, and released during black hole evaporation in full detail. We do not know whether holography applies to our universe in a direct way, or whether it is a guide pointing toward a broader principle. We do not know whether gravity is fundamentally emergent, or whether emergence is only part of the story. We do not yet possess a complete theory of quantum gravity. What is striking is how constrained the unknowns are. Black holes have eliminated vast classes of possibilities. Any future theory must reproduce known thermodynamics. It must preserve information. It must reduce to general relativity at large scales. It must explain why entropy scales with area. These requirements are not optional. They are enforced by nature. This chapter is not about resolving uncertainty. It is about respecting it. Physics advances not by pretending to know more than it does, but by carefully marking the boundary between knowledge and ignorance. Black holes have pushed that boundary forward, not by providing answers, but by sharpening the questions. The distinction between what is known and what is unknown is especially important in a field where speculation can easily outrun evidence. Gravity invites bold ideas, but it also demands discipline. The history of physics shows that progress comes not from dramatic claims, but from ideas that survive contact with constraints. black holes have provided some of the strongest constraints ever discovered. One thing we know with confidence is where classical descriptions fail. General relativity predicts its own breakdown at singularities. These are not physical objects, but signals that the theory has been pushed beyond its limits. They tell us that spacetime cannot be treated as infinitely smooth under all conditions. Any theory that claims to replace general relativity must resolve this failure without discarding the theory's successes. We also know that semi-classical approaches have limits. Treating spacetime as classical, while quantizing matter, works extremely well in many settings, but black hole evaporation exposes its shortcomings. The information problem does not arise from speculation. It arises from applying trusted tools exactly where they are no longer sufficient. This tells us not that those tools are wrong, but that they are incomplete. Another area of partial knowledge lies in entropy bounds. The fact that black hole entropy sets an upper limit on the information content of a region is one of the clearest results to emerge from this field. It has been tested indirectly through consistency arguments across gravity, quantum theory, and thermodynamics. While we do not know why this bound exists at a microscopic level, we know that it cannot be violated without breaking fundamental principles. There is also growing agreement about what will not work. Simple modifications of gravity that ignore entropy and information fail quickly. Proposals that allow information loss lead to inconsistencies in quantum theory. Models that treat black holes as ordinary objects without thermodynamic behavior contradict well-established results. These dead ends are valuable. They prevent wasted effort and focus attention where it belongs. At the same time, it is important to recognize what remains genuinely open. Different approaches to quantum gravity offer partial insights, but none has yet delivered a complete description that applies to our universe in all regimes. Calculations that succeed in idealized models do not automatically generalize. Mathematical elegance alone is not enough. Nature demands empirical consistency. This balance between confidence and uncertainty defines the current state of the field. Gravity is not mysterious because we lack ideas. It is mysterious because the ideas must satisfy exceptionally strict conditions. Black holes have made those conditions explicit. They have narrowed the search space and clarified the standards any future theory must meet. Recognizing these limits is not a weakness, it is a strength. It prevents false certainty and keeps inquiry grounded. Gravity remains unresolved not because it is unknowable, but because it is subtle. The clues are present. They are consistent. They simply point beyond our current reach. The final piece of clarity comes from understanding why these unanswered questions matter. Gravity is not an isolated problem. It connects to the origin of the universe, the fate of matter, and the structure of reality itself. Any incomplete understanding of gravity leaves gaps elsewhere. The early universe, where densities were extreme, cannot be described fully without quantum gravity. The ultimate fate of black holes cannot be understood without it either. What black holes have taught us is that ignorance is not uniform. We do not face a fog of uncertainty in all directions. We face a sharply defined frontier. On one side lies well-tested physics. On the other lies a narrow set of possibilities, constrained by thermodynamics, information, and consistency. This is not confusion. It is progress. The absence of a final theory does not mean gravity is hiding the truth. It means the truth is layered. Classical gravity describes one layer with extraordinary success. Thermodynamic behavior reveals another layer beneath it. Quantum effects hint at deeper structure still. Each layer is valid in its domain. None can be discarded. This layered view explains why gravity feels different from the other interactions. Electromagnetism and the nuclear forces operate within space-time. Gravity shapes space-time itself. It is both background and participant. That dual role makes it resistant to simple unification, but also makes it uniquely informative. Black holes are the places where all these layers intersect. They are not exceptions that break the rules. They are the regimes where the rules reveal their full implications. They do not obscure understanding, they sharpen it. By separating what is known from what is unknown, the picture becomes clearer, not emptier. We know enough to say with confidence that gravity cannot be fully understood without entropy. We know that information is central, not incidental. We know that spacetime is not the whole story. What we do not know is the final form these insights will take, whether gravity emerges entirely from information or whether information itself emerges from something deeper, remains open. Whether spacetime is fundamental or effective is undecided. These questions are not failures. They are the active frontier of research. Science advances by respecting such frontiers, not by filling them with certainty, but by exploring them carefully. Black holes have defined the frontier of gravity with remarkable precision. They have shown us where to look, even if they have not yet shown us what we will find. Gravity began as something intimate and unquestioned. It was the certainty that objects fall, that the ground waits beneath our feet, that the sky does not drift away. Long before equations or theories, gravity was learned through experience. It felt permanent, reliable, and complete. And for centuries, physics treated it that way, a force to be measured, predicted, and eventually understood. But as gravity was followed carefully into the depths of space and time, it refused to remain simple. Each attempt to pin it down revealed another layer. Geometry replaced force, curvature replaced attraction, time itself bent under its influence. And when gravity was pushed to its most extreme limits, at the edges of black holes and the beginning of the universe, it exposed fractures in our understanding that could not be ignored. What emerged from those fractures was not chaos, but structure. Black holes did not destroy the laws of physics, they enforced them. With ruthless precision, they demanded that gravity obey thermodynamics, respect information, and remain consistent with quantum theory. In doing so, they transformed gravity from a solved problem into a guide toward deeper principles. One of the most important lessons is that entropy is unavoidable. Wherever gravity becomes strong enough to form horizons, entropy appears, not as a metaphor, not as an analogy, as a physical quantity with exact mathematical form. Horizon area behaves like entropy. Surface gravity behaves like temperature. These relationships are not optional decorations on general relativity. They are demanded by consistency. This fact alone reshapes the nature of gravity. Entropy is never fundamental. It always emerges from microscopic degrees of freedom. When entropy appears in spacetime itself, it implies that spacetime is not the deepest layer of reality. The smooth geometry described by general relativity behaves like a macroscopic variable, accurate and powerful, yet blind to the details beneath it. This does not diminish general relativity. It explains its success. Just as thermodynamics works without knowing the motion of individual molecules, general relativity works without knowing the microscopic structure of spacetime. Its equations describe averages. They capture large-scale behavior. They do not reveal the underlying constituents. Black holes make this unavoidable. Their entropy is enormous, far greater than that of ordinary matter. Gravity is capable of storing information at densities that no other interaction can match. This tells us that gravity is not merely responding to matter, it is regulating information itself. Once this is accepted, gravity can no longer be treated as an isolated interaction. It becomes part of a broader framework linking geometry, thermodynamics, and information. Horizons are no longer just boundaries in space. They are boundaries of knowledge. They separate what can be observed from what cannot. And in doing so, they generate entropy and temperature. Hawking radiation completes this picture. Black holes are not eternal. They evolve. They exchange energy with the universe. They slowly evaporate. This forces the question of information into the open. If black holes can disappear, then whatever they store must be accounted for. Either information is preserved in some subtle form, or the foundations of quantum mechanics must fail. Nature has already narrowed the options. Information loss leads to contradictions that ripple through physics. Simple fixes collapse under scrutiny. The remaining possibilities are constrained, delicate, and deeply non-classical. They point toward a description of gravity in which space-time itself is emergent. Yet emergence does not mean illusion. Temperature is emergent, yet it is real. Pressure is emergent, yet it shapes worlds. Gravity, even if emergent, governs the structure of the universe with unquestionable authority. Its emergence would explain its universality, its weakness at small scales, and its resistance to quantization. What black holes have shown us is not the answer, but the shape of the answer. Any future theory of gravity must reproduce black hole entropy exactly. It must preserve information. It must reduce to general relativity where tested. And it must explain why space-time behaves thermodynamically in the presence of horizons. These are not optional goals. They are requirements imposed by reality itself. Gravity is not hiding the truth. It is revealing it slowly through the most extreme environments the universe can produce. Black holes are not failures of theory. They are stress tests. And gravity has passed those tests not by remaining simple, but by pointing beyond itself. Gravity has led us to a place where certainty gives way to constraint. We do not know the final theory, but we know what it must respect. This alone is a rare position in science. Often, ignorance is broad and unstructured. Here, ignorance is narrow and sharply defined. Black holes have carved boundaries around what gravity can and cannot be. One of the clearest boundaries is information. The universe does not allow information to simply vanish. This is not a belief. It is built into the structure of quantum mechanics. Every successful prediction in quantum theory relies on unitarity, on the idea that the present always contains the past in encoded form. Black holes challenge this principle not by defying it outright, but by forcing us to confront how deeply it is woven into reality. The classical picture of space-time suggests that regions can become causally disconnected forever. Horizons form. Interiors become hidden. From the outside, information appears gone. But this appearance cannot be the whole story. If it were, quantum mechanics would unravel. The consistency of the universe demands a deeper explanation. This is where the role of horizons becomes central. Horizons are not merely geometric curiosities. They are interfaces between descriptions. To one observer, information falls inward and disappears. To another, it is absorbed and thermalized at a boundary. These descriptions do not contradict each other. They are complementary. Each is incomplete on its own, yet together they preserve consistency. This idea forces a profound shift in how reality is described. Classical physics assumed a single objective picture of events. Black holes suggest that such a picture may not always exist. Instead, different observers may require different descriptions, each valid within its domain. Information is not duplicated, but it is not localized in the classical sense either. Such ideas are uncomfortable because they stretch intuition. But they are not arbitrary. They arise from demanding that well-tested principles remain intact. Gravity does not grant permission to abandon quantum mechanics. Quantum mechanics does not allow gravity to ignore information. The resolution must satisfy both. This mutual constraint is what makes black holes so powerful. They are not merely extreme objects. They are consistency engines. They expose contradictions that would otherwise remain hidden. They demand reconciliation where theories overlap. Another boundary black holes impose is on locality. In ordinary physics, causes influence nearby effects. Signals propagate step by step through space. Black holes suggest that this picture may break down subtly at fundamental scales. Information may be encoded non-locally, spread across correlations rather than stored at points. This does not violate causality in observable ways, but it challenges the idea that space-time points are the fundamental carriers of physical reality. The holographic principle captures this shift elegantly. It suggests that the deepest description of a region of space may live on its boundary, not as a visual projection, but as a complete encoding of information. Geometry becomes secondary, volume becomes emergent. What matters fundamentally is how information is organized and entangled. Yet even holography does not close the story. It works beautifully in certain idealized settings, but our universe is more complex. It expands, it accelerates. It lacks the symmetries that make holographic models exact. This does not invalidate the principle. It means the principle is incomplete. Still, the lesson remains. Gravity is deeply tied to information. Any attempt to describe spacetime without accounting for information, flow, and entropy will fail. The universe has made this clear. This realization also reframes the search for quantum gravity. The goal may not be to quantize spacetime directly, but to understand the quantum system from which spacetime emerges. Geometry may be the collective behavior of something more fundamental, just as sound is the collective behavior of vibrating matter. If this is true, then many puzzles about gravity find natural explanations. Its weakness at small scales reflects the fact that collective behavior requires many degrees of freedom. Its universality reflects the fact that information underlies all physical systems. Its resistance to unification reflects the fact that it is not a force like the others. None of this is proven, but none of it is arbitrary either. Each step is guided by evidence, by consistency, and by the refusal of black holes to let contradictions slide. What we are left with is a picture that is incomplete yet coherent. Gravity is not fully understood, but it is no longer mysterious in the way it once was. The mystery has shape, it has boundaries, it has rules, and that changes everything, because knowing the shape of a problem is often more important than having its solution. Gravity does not conclude with an answer, because gravity is not a question that can be closed. What it offers instead is a framework for understanding why certain answers are impossible to reach too quickly. This restraint is not a weakness of science. It is one of its most powerful features. The universe does not reward certainty where certainty is not earned. It rewards consistency, patience, and respect for limits. When we look back at how gravity has guided physics, a pattern becomes clear. Every time gravity was thought to be fully understood, it revealed a deeper layer. Newtonian gravity unified Earth and sky, then failed quietly at high precision. General relativity replaced force with geometry, then revealed horizons and singularities where geometry itself lost meaning. Black holes introduced entropy and temperature, forcing thermodynamics into spacetime. Hawking radiation forced quantum mechanics into the heart of gravity. Each step did not invalidate what came before. Each step exposed where the previous description stopped being sufficient. This is why gravity feels different from other interactions. It is not just another force to be catalogued, it is the framework in which all other forces operate. When gravity bends spacetime, it bends the stage on which physics unfolds. When gravity creates horizons, it creates limits on observation itself. No other interaction does this. No other theory carries such implications. Black holes make this unavoidable. They are not extreme because they are rare. They are extreme because they strip gravity of all distractions. They remove structure, complexity, and detail until only the core principles remain. What survives that stripping is what must be fundamental. Entropy survives, information survives, geometry survives only as an effective description. This is why black holes are not obstacles to understanding. They are filters. They remove false assumptions. They discard ideas that cannot survive consistency. They force theories to reveal what they truly depend on. One of the most difficult lessons they teach is that intuition is unreliable at fundamental scales. Human intuition evolved in weak gravity, low curvature, and slow motion. It is not equipped to reason naturally about horizons, quantum entanglement, or emergent space-time. Expecting intuitive clarity in these regimes is a mistake. Physics progresses precisely when intuition is replaced by disciplined reasoning. This is also why metaphor must be handled carefully. Saying that space-time is a hologram or that gravity is an illusion can be evocative, but it risks obscuring what is actually known. The evidence does not say that space-time is fake. It says that space-time may not be fundamental. There is a crucial difference. Emergence does not imply unreality. It implies dependence. Temperature depends on microscopic motion, yet it is real. Pressure depends on particle collisions, yet it shapes worlds. Sound depends on vibrations, yet it carries meaning. If space-time depends on information, it is no less real for that dependence. Gravity, even if emergent, governs the universe with absolute authority. What black holes suggest is not that gravity disappears at deeper levels, but that it changes language. At large scales, geometry is the right language. At deeper scales, information may be the right language. Both can be true simultaneously. Neither needs to eliminate the other. This layered description is uncomfortable because it resists reduction to a single picture. Physics has often succeeded by reducing phenomena to simpler constituents. Gravity resists this strategy, not because it is beyond understanding, but because it may already be an emergent description. Trying to reduce an emergent phenomenon directly leads to confusion. One does not reduce temperature by quantizing heat. One reduces it by understanding particles. The same may be true for gravity. Quantizing space-time directly may be like quantizing waves on the surface of an ocean without understanding water molecules. The waves are real, they matter, but they are not fundamental. This perspective also clarifies why gravity has remained so difficult to unify with other forces. The electromagnetic and nuclear interactions operate within space-time. Gravity defines space-time. Expecting them to merge symmetrically may be misguided. Gravity may belong to a different category entirely. Black holes sharpen this distinction. They show that when gravity dominates, the usual separation between matter, energy, and geometry breaks down. Energy becomes geometry. Geometry becomes entropy. Entropy becomes information. The boundaries between concepts blur, not because the universe is vague, but because the concepts were never meant to be fundamental in isolation. This is not a call to abandon mathematics or precision. On the contrary, the progress described here is deeply mathematical. The relationships between entropy and area are exact. The derivations of Hawking radiation are precise. The constraints imposed by unitarity are non-negotiable. The mystery is not a lack of rigor. It is the presence of too much rigor, pointing beyond current frameworks. This is also why speculation must remain grounded. Many ideas about gravity sound appealing, but collapse when tested against black hole thermodynamics. If a proposal cannot reproduce horizon entropy, it fails. If it allows information loss, it fails. If it violates well-tested limits, it fails. Black holes do not tolerate inconsistency. In this sense, gravity is already teaching us how to proceed. It tells us to build theories that are conservative, where evidence is strong and bold, only where constraints allow. It tells us to respect thermodynamics as deeply as we respect symmetry. It tells us that information is not a bookkeeping tool, but a physical ingredient. The absence of a final theory is not an absence of direction. The direction is clear. Any future understanding of gravity must explain why space-time behaves thermodynamically, why entropy scales with area, why information is preserved, and why geometry emerges at large scales. These are not optional goals. They are the minimum requirements. Whether the final theory will resemble current approaches or introduce entirely new ideas remains unknown. It may involve quantum information in ways we do not yet recognize. It may require new mathematical structures. It may force us to rethink what we mean by space and time. But whatever form it takes, it will not erase the lessons learned here. It will incorporate them. Gravity without final answers is not a failure of explanation. It is a mature understanding of where explanation ends and structure begins. The universe is not obligated to be simple in the way we prefer. It is obligated only to be consistent. Gravity has shown us that consistency leads to depth, not closure. Black holes are not warnings against inquiry. They are invitations to humility. They remind us that nature reveals itself gradually, under pressure, and only when asked the right questions. They show us that the most profound truths are often not statements, but constraints. In the end, gravity has done something remarkable. It has taken the most familiar aspect of experience and transformed it into the deepest guide we have to reality's foundations. It has connected falling objects to cosmic horizons, geometry to entropy, and motion to information. It has shown us that understanding does not always mean knowing what something is, but knowing what it must obey. The truth about gravity may not be hidden behind a final equation. It may be distributed across principles that refuse to be violated. Entropy must increase. Information must be preserved. Geometry must emerge. Horizons must behave thermodynamically. These are not answers, they are anchors. And anchors matter. They keep understanding from drifting into fantasy. They give future theories something solid to attach to. They ensure that progress remains tethered to reality. Gravity, then, ends not with certainty, but with coherence. Not with resolution, but with alignment. The universe has shown us enough to know that the question is meaningful, the path is constrained, and the destination, while unknown, is not arbitrary. That is not an ending. That is an honest stopping point. And it is exactly where real science lives.